Hello, everyone. I'm here to introduce Fernando Castro. He is an application scientist at Gatan. To give you a little information about Fernando, he received his Ph.D. in material science and engineering from Northwestern in 2018. And since then, he's been at Gatan ever since. Fernando is currently supporting our imaging and diffraction product lines like the ClearView camera, and he focuses both on customer training and new product development. So I'm going to go ahead and let him run with the presentation and go from there.
All right, good morning, everyone, or good afternoon. Hello, thank you so much for joining. My name is Fernando Castro. I just wanted to finish with a little bit of housekeeping, and that's if you have any questions throughout the presentation, please submit them through the questions pane that you see in the GoToWebinar interface. If you have any issues with connectivity, you can also type it in there and someone will reach out and help you. And we'll address the questions at the end of the presentation. Without further ado, let's get started. This morning, I'm going to talk about advances in scintillator camera technology for modern transmission electron microscopy. So what that really means is that in today's presentation, I'm going to try to address a couple of questions about scintillator cameras and how we can use them for all sorts of different kinds of microscopy applications and techniques that people want to do today. So the first thing I'll talk about is what kind of technology is actually powering scintillator cameras today, specifically with respect to what's the sensor technology that we're using in scintillator cameras. And once we understand that, the other thing that's important to understand is what kind of electron microscopy challenges are we trying to solve or do we currently face today with modern scintillator cameras, and how do the technology that is powering the scintillator cameras and the electron microscopy challenges that we face link up together to help define what we're trying to do differently with the development of new hardware features and new software features for these cameras that we use for all sorts of electron microscopy, specifically within the TEM. So the most fundamental thing I think to understand about a scintillator camera is the idea that it uses an organic scintillator material, here shown in purple, that gets hit by the electrons coming from the electron microscope and generates light. This light is then, through some mechanism, transferred to the sensor, where the sensor takes an analog signal, converts it into a digital signal, and then helps form an image on the computer and gives you all sorts of data that we can then process and do the kinds of analysis that we want to do. The only other thing I'll mention is that how we move the light from the scintillator to the sensor is very important. At Gatan, we do fiber optic coupling, but that's just sort of an aside for, I think, what is the main idea of the presentation and what we'll be talking about, which is the sensor technology used in these scintillator cameras and how that affects what's possible in terms of microscopy techniques and achievable sensitivity, speed, etc. So a good place to start, I guess, is the CCD sensor type of technology, which I think many people are familiar with or have heard this term or even use the term colloquially to describe the kind of camera that they may have on their microscope. And with the CCD camera, what's important to understand is essentially how the charge readout process worked and what effect that had on the camera function. So when the light comes from the scintillator that I showed in the previous slide and hits a pixel, it generates some charge here in the pixel. And for it to form a digital image, you actually, with a CCD camera, had to physically move the charge from pixel to pixel to pixel to pixel to the specified area of the sensor where it could read out and form this, take this built-up charge from the pixel, convert it into a voltage, and then that into a digital signal. And so the idea is that moving all this charge around across the full area of the sensor was a slow process. And normally with a CCD sensor, when you read out the signal from the camera, it operated in what's called a global shutter mode, which some people may have heard of. The idea being that the entire sensor area gets read out at once after all of the charge from the pixels gets moved to the readout area of the sensor. And this global shuttering mode and this CCD readout mode was slow. And so it had a real world important practical effect in a negative way on what we could do in terms of speed and advanced experiments with the camera. Now, CMOS sensors, which are essentially pretty much the only technology used in the market for electron microscopy scintillator cameras, had a very different pixel design where the light could hit a pixel, but then the process of forming a digital signal from the analog charge that gets formed at the pixel happened within the pixel. It was a much more complicated pixel design with more transistors, and that meant that you didn't have to move charge around anymore before you can convert it into a digital signal and read it out. And so because you removed this slow process of moving charge around that you had with the CCD, with the CMOS sensor, you could read out pixels much, much faster. And now you can start doing things, reading out the sensor in faster, more complicated ways, often referred to as a rolling shutter mode, which here you see you could read out row by row very quickly instead of the entire sensor at once. And even this is a dramatic oversimplification of what kinds of things you could do in terms of readout strategies for the sensor to improve the speed of the camera to benefit the kind of microscopy that we're trying to do. And so back in the CCD era, which here I just generally label as in like the 2000s, there were a couple of challenges that people faced when using a CCD camera. One of them was the trade-off that you always had to make multiple times throughout your experiment of having a high frame rate with a low image size or a large image size with a low frame rate. This meant that you could capture really nice high resolution images at frame rates that were far too slow to really move the sample around in. And I'll show some more numbers on this in the coming presentation. But if you wanted to have moderate frame rates to do anything, for example, in situ related or navigating around on your sample, then you had to dramatically reduce the image resolution that was possible from the camera. The other thing that was a challenge commonly because of the slow readout from the CCD era sensors was the fact that if you had sample drift during imaging, there was no real way of reducing that that effect of the sample drift in your image unless you sat there and waited for your sample to stabilize for however long it took. You know, if you only had the capability to read out an image, once a second or even slower, so sample drift was a significant annoyance and problem in many kinds of experiments. And then, of course, if you want to do anything in situ related at all, slow speed was not good. You couldn't read out information at the speeds required to capture the dynamic reactions going on in your experiments many times. And so often there was some workaround involved of doing screen recording of the live view of the camera or some other mechanism to try to improve the frame rate or of your data, often at the cost of affecting the kind of image resolution that you could have or completely throwing away the metadata coming from the camera because you were just recording a screen that had none of that information. And so these were really three big problems that came about practically from the fact that we were using the best at the time, but still a slow CCD-based sensor. And in 2014, Gatan introduced the OneView camera, which was the first camera that offered a higher speed CMOS camera for a Scintillator camera that was available from Gatan at the time. And so the OneView camera moving to the CMOS camera technology effectively solved all of the three problems that we just talked about in the previous slide. The idea that you had to do a trade-off between camera speed and resolution was solved because the high-speed CMOS sensor meant that you could both read out a larger image size, up to 4K by 4K in image size, at a good frame rate of 25 frames per second. And so you didn't have to move back and forth between an imaging mode and a sample navigation mode on the camera. You always had the capability to do both. The other thing that this got rid of was the sample drift during imaging, because you could do live drift correction of the images as they came off the camera sensor. And I'll talk a little bit more about how we do that later in the presentation. And then if we wanted to do in situ data capture, you didn't have to do any kind of awkward screen recording anymore, because the OneView speeds could record up to 300 frames per second and record the raw data with all of the associated metadata directly to the computer. And so it was way easier to do an in situ kind of experiment with a faster camera like the OneView camera. There are also a couple of other advantages that were really important that came with having a large area. One thing about the OneView was that we had a pixel design in terms of the pixel size and a bunch of other details that matched the point spread function of the camera as well. And so you could collect large area high resolution images just like this one. It's a gold cross grading sample. But if we look at the FFT of this image, we could see that we could detect in this case, this is the gold 111 sort of ring from the FFT, but you could detect this FFT information essentially to the edge of the FFT of the image, which means that you could detect information at high resolution and lower magnification to the limits of the Nyquist frequency of the experiment and of the camera. And so this meant that you could acquire images that were a large field of view that were still high resolution in both of information that you could see in the FFT and also information that you could see in the image itself. And so this was another just big advantage in general of moving to this newer sensor design. But I think the big thing that really came about was also in speed. And so here on this table, I'm showing 3 different cameras from Gatan. In the CCD era from Gatan, 2 really popular cameras. One was the Ultrascan camera, the other was the Arias camera, and then we had the OneView camera. And what I'm showing here is the image, the largest image size you can get from the cameras, the frame rate at that image size, and then also what's the maximum frame rate you could get out of the camera, regardless of what image size you used. And so if we look at the OneView camera, the switch from CCD to CMOS enabled both a larger sensor that you would have and also faster frame rates compared to our Ultrascan camera and our Arias camera, both of which were good cameras, but just lacked the speed to support a higher format image and also a high frame rate capability. And so you may have heard this in the past, but when you can do 4K by 4K imaging at 25 frames per second, that really is a live view experience of seeing information come from the camera and displayed on the microscope at rates that make sense and that mirrored what you could get if you were just looking, for example, at the phosphor screen on the microscope, if you still have a microscope with a phosphor screen even. And so because you had high resolution in terms of image size and high speed, you can do things like drift correction, which I mentioned a couple of slides ago. The way this worked was the fact that a CMOS sensor, because it wasn't doing the global shutter mode anymore, actually read out in a different way. So if you said I wanted a 1-second capture, it would, at 25 frames per second, the CMOS camera would give the computer, would read out 25 individual frames that would get summed together into one final output image for the user to then take and do whatever kind of analysis. But because you had the individual 25 frames coming off of the camera, you could align all of those frames before they get summed together into the final output image. And this meant that you could do drift correction on data in real time as you captured the images. And that's something that just wasn't possible with a CCD camera, because you would only get one frame coming off the camera at whatever frame rate that you defined. And so the difference with drift correction, can be really large. This is just an image of some particles in the sample, but we all know what a drifty image looks like. And then under the same conditions with the drift correction turned on the camera, you could align all of these frames and then get a really nice lattice image of the same particles at the same drift rate. So that's one benefit that came out of having high speeds at a large image size. But the other benefit that is important also was, as I've been talking about, was in situ. So if we wanted to do some kind of high speed in situ experiment, the Ultrascan could go 5 frames per second, which was not very good for an in situ experiment. The Orion could go 30 frames per second, which is better, but had the trade-off still of you needed a 512 by 512 image. And so the OneView could actually go at the same image size, 300 frames per second. And so although you still had a small image, you had a dramatic increase in the frame rate capabilities coming off the camera, which meant that you could better resolve faster changes in some kind of dynamic reaction that you wanted to study in situ. On top of that, in the 2014, 2015, 2016 kind of timeline, 4D STEM started coming out and emerging as a very popular technique. And so the acquisition speed of 4D STEM, which I'll talk about later, is dependent on what your camera frame rate is. So any increase in the frame rate that you could get from your camera was huge for 4D STEM in terms of acquisition speed and throughput of the kinds of analysis from this new emerging technique at the time. And so when you have high speed capabilities with the OneView, you can start doing really cool things. One example is here in this video here. This is just looking at different particles moving across the screen, the edge of this cerium oxide. So if you look at the different facets of this particle on the edge, you can see that there's small little atoms moving around on the edge of the cerium oxide particle, which is a cool experiment that you could do and resolve with a high-speed camera, like a camera, the OneView, that had a CMOS sensor as opposed to a CCD sensor. And then, of course, I mentioned that we also could start doing 4D STEM. And so with 4D STEM, you can acquire a data set and do all sorts of kinds of analysis, like virtual bright field and dark field imaging, and then also strain mapping on your samples. And I'll talk about more about 4D STEM later as well. But the high speed of OneView was a nice thing. Then once, of course, the pace of development and applications development and technique development never stops. And so in the late 2010s, early 2020s to now, there were new challenges that emerged in the microscopy field of what people were trying to do with their Scintillator cameras. The first, I think, big challenge that I came across was the fact that people wanted better data quality for imaging and diffraction experiments coming off of the camera. And so one thing was that because you could start doing drift correction and you always had a live view and the camera in general was pretty easy to use, people really quickly started trying to push the camera to its performance limit in terms of speed and sensitivity and doing low dose imaging experiments, or diffraction experiments. And it very quickly became obvious that they wanted a way of getting better quality data, less noisy data out of the camera. The other thing was that people got really interested in doing experiments on beam sensitive materials that required low doses or low dose rates, and they wanted to be able to get better signal to noise from their data from their Scintillator camera under these low dose conditions. And then the third thing that sort of emerged at that time was evolving diffraction techniques that required higher dynamic range. So that meant both, 4D STEM capabilities, but also people are really interested in the biological space, also in micro-ED for doing structural determination. And so across a wide area of applications, people started focusing more and more on diffraction again. And the higher dynamic range that you have on your camera meant that you could better resolve in high intensity spots and weak intensity spots and improve the analysis that you get from the camera. And then the other thing that emerged was not only just that people wanted better data quality, but people still wanted higher speed and higher throughput for advanced experiments. And so one of those things was that in the in situ world, if you wanted 300 frame per second imaging, for example, with the OneView, there was still a pretty significant trade-off in terms of what image resolution you could use. You had to go from 4K by 4K images all the way down to 512 by 512. And so that isn't necessarily still very useful for some experiments. And then again, 4D STEM really took off as an application, and people want to do 4D STEM a lot now. And your throughput in 4D STEM is bottlenecked by the achievable frame rates of the camera. So a faster camera means faster 4D STEM acquisition and faster time to results. And so this was all things that people sort of, when they had a OneView camera or other CMOS type cameras in the market, this is what people often came to me and other people at Gatan for solutions on how to improve. And so about a year and a half ago now, we released the ClearView camera, which was the successor of the OneView camera. It's the camera that elevates your microscopy potential. It's the best-in-class scintillator camera that we built on the innovations from the OneView camera. And I think what it really does is it tries to deliver on the last two challenges really well. The first thing it has is this new frame control mode, which I'll talk about in detail, but it's a mechanism of running the camera to improve the signal to noise of your image and diffraction patterns that you capture with the camera. And then the second thing it does is it has a brand new sensor, still CMOS based, but that allowed even faster readouts. So we can go up to 1600 frames per second, which is the fastest frame rate of any Scintillator camera available, as far as I know. And that's great for 4D STEM and then also high-speed in-situ experiments as well, which I'll talk about more in detail. So the first thing I'll talk about was how we can use these new mechanisms for running the camera in this frame control mode to maximize your signal to noise. So one thing that's important to understand as just background as we go into this discussion is read noise and how that affects your signal to noise in your images. So I talked about with the OneView, and the same holds true for the ClearView camera and essentially a lot of different CMOS cameras. The idea is that if you're outputting all of the individual frames at this frame rate, say with the OneView at 25 frames per second, and then you sum them into one image, each individual frame has a certain amount of noise, intrinsic noise, called readout noise. And so when you sum a lot of frames together, the amount of read noise that you get into your final image depends on how many individual frames you actually added up together. So if you had 50 frames per second in a 1 second capture, say you had 50 units of read noise that you integrated into your final image, and that affected your signal to noise ratio of the data coming off of the camera. What the ClearView camera can do is it has this frame control mode, which lets you choose what frame rate you want to use on the camera. And actually, you can run the camera super slow if you really wanted to improve the signal to noise by just integrating less read noise into your final image. And so the idea is that instead of always running at one frame rate, which is what the OneView camera had to do, you could control what frame rate you want and optimize for the signal to noise. So the camera, although it can always run at this high speed of 50 frames per second at 4K by 4K images, which I'll show on the next slide, you could also run it at 2 frames per second to integrate very little read noise and use a longer exposure time to maximize the signal to noise ratio in the data that you acquire, whether it's an image or a diffraction pattern, etc. And so just like I was saying, with the OneView camera, you had an image, if you ever used a OneView camera, you had an imaging mode and a diffraction mode, and each mode had a fixed frame rate. And so if you wanted to improve the signal to noise in your data, all you could really do was increase the signal by increasing the amount of electrons on the camera and increasing the dose on the camera and on your sample. And so this isn't really useful if you want to do a low dose kind of experiment. The ClearView gives you the frame control option here, which I show at the bottom. So the UI is very similar, and you have this new frame control option. And you can essentially pick between whatever the max frame rate is for the camera at the given imaging mode and 0.033 frames per second, which is 30 seconds per frame exposure time. And so if you had a really, really low dose, for example, like diffraction experiment, probably, you could use the frame control mode here to integrate way less read noise into your data compared to operating the camera in its full speed or operating the OneView camera in either the imaging mode or the diffraction mode. And so this has real world effects very quickly on the data, whether it's imaging data or diffraction data. And so this is an example here of what data from the ClearView camera looks like with this frame control mode. This is just a semiconductor sample. On the left, it's a 50 frame per second image, which is the standard maximum frame rate for the camera at 4K by 4K resolution. And we have a 2-second capture. So this means that you've integrated 100 frames together into this final output image to get the image here in the middle. And you can see a lot of features here, but I think you can also see that it can be a little grainy. And if you wanted to look at interfaces here, in whether it's in this semiconductor sample or literally any other kind of sample, it can be kind of hard, especially in this top example here, or this top area, to see, where is the start and end of some kind of interface. And so when you have the frame control mode, for example, on the right, this is 1 frame per second at 2 seconds total capture. So this is 2 frames integrated into this final image as opposed to 100 frames. And I think in general, it's a lot less grainy, meaning that it's a lot less noisy of an image. And you can see these sharp, or not sharp, but you could see these interfacial features that we were interested in much more clearly than we could at 50 frames per second. Especially down here, you can see that there's some interface here maybe that we were really interested in resolving that we couldn't quite see at the higher speeds. And so having the ability to adjust the frame rate to match your imaging requirements for signal to noise is super useful with the frame control mode. Here's another example of a low beam dose condition from the ClearView camera. So this is a single frame exposure, so 0.02 seconds from the ClearView camera. And this is obviously a very noisy kind of image and wouldn't make very good data. And but it's the kind of imaging condition that is required if we want to do some low dose imaging on a sample. So one of the best ways of just acquiring at this low dose rate condition is by using a longer exposure time, and then also minimizing the frame rate that you use to minimize the amount of integrated read noise into your data and maximizing your signal to noise. And so this is what the image looks like with ClearView when you are at 5 frames per second for a 5 seconds exposure, so 25 total frames. And I think it's a quite nice image that you're able to recover actually from this noisy image on the left of a single frame that comes from the low dose condition. And so because again, this is a 4K by 4K camera, just like the OneView, we can zoom in on a smaller area and still see really fine lattice detail here on the right of the image, which is a really great ability to take a low beam dose condition, a low dose rate condition, and still get good images from your sample from a Scintillator camera. So in comparison to the OneView, a lot of people ask, how much different is this mode with the ClearView compared to the OneView? So this is the OneView camera image under the same exact dose conditions, same exact exposure time, running at 25 frames per second, which is the only mode, the only frame rate you can run at with the OneView when you're in imaging mode. And so you get an image where it's actually, you can still see similar kinds of contrast and features as before, but if we look closely, you can see that there's all sorts of vertical lines in the image, and that's integrated noise into noise that's integrated into the final image as a result of having a lower signal to noise in the data itself. Again, here's on the right now that I'm showing the ClearView image from the previous slide, and you can see the differences between the two in terms of the level of noise. And if we look at the FFT specifically as well, you can see this noise in the FFT pop up here in this horizontal and vertical line in the FFT, which you don't see with the ClearView camera because we've optimized the imaging condition with the frame control mode here. So you get better, less noisy results from the ClearView camera with the frame control than you could with the OneView camera. So that's a really important result for folks who are interested in doing low dose rate, low dose experiments with the ClearView camera. And so the best thing that you can also do is still combine the frame control mode with the drift correction that we talked about previously, because we're still outputting multiple frames per second in our image capture. So if this was what our image looked like in the FFT with no drift correction, notably, you only kind of see the 111 ring from the gold here in these two corner positions, and not in the other areas here, say at this 11 o'clock position, at this 5 o'clock position. And that's a result of drift in the image. And so when you apply drift correction to the imaging under the same conditions, now you can see the 111 gold ring all the way around in all directions, which means that we've effectively got rid of all of the drift in the image, and we can see high resolution information in all directions. And you can also see that when you have drift correction, you can start seeing even higher resolution rings here in the diffractogram, which is really nice. So you can acquire, with drift correction and frame control, really nice high resolution, high signal to noise images with the ClearView camera. Now it's also a good effect on diffraction experiments as well. And so when we have, again, this is what the ClearView camera looks like. If we turn on the frame control mode to show you again, this is again just gold, but we're showing here the difference in this diffraction pattern at 200 frames per second, which you can achieve with binning on the camera, or 50 frames per second. And you can see a lot of rings in this pattern, but what I want to point out to you here on the left is what the background looks like. And you can see that at 50 frames per second, the background looks darker than at 200 frames per second. And it's easier to see that as well if we look at the line plot here. This plot is a radial intensity distribution of this diffraction pattern. And we're looking at what the difference is here using different camera frame rates on the background levels of the data, and how that affects the visibility of different diffraction rings or peaks within the data. And importantly, at 200 frames per second, for example, this is the green filled area here. We can see some features, of course, at higher resolution in reciprocal space. But as we decrease the frame rate, which means that we decrease the amount of total noise integrated into the data, we can see that the background level drops and that these higher resolution rings or peaks in diffraction pattern become much more visible. Specifically here at 0.35 angstroms in this data here, you can start seeing this peak in this green line here much better than you could at 200 frames per second here in comparison. So the real world effect of having the frame control mode in diffraction experiments is that you can start seeing fainter spots much better over the noise floor of the data that is captured. Here's another nice comparison with the OneView camera and the ClearView camera. So on the left is a diffraction pattern from the OneView camera. The camera is running in diffraction mode. And on the right is from the ClearView camera, and I'm running it at 1 frame per second and 5 seconds exposure here. So there's, some people may say, what's the contrast limits? Are the contrast limits the same? Yes, they are the same, and they were determined based off the OneView diffraction pattern here that we're showing on the left. And so there's one thing you can see, I think, clearly is that the spots and thing in general in the pattern on the right with the ClearView are much brighter, and you can actually discern this ring here from the gold in the ClearView pattern that you cannot see at all over the noise in the diffraction pattern from the OneView camera here. So you can see higher resolution information with the ClearView camera at the same dose rates because you have this frame control capability. And also, you have some other advantages of the ClearView camera over the OneView camera in diffraction mode. And one of those is the dynamic range of the camera. So as one more example of the frame control mode here with the ClearView, this is a diffraction pattern of just, silicon 110. It's really basic, but I've captured this image at 4 frames per second for 1 second total exposure time. And so, okay, we can say this is a nice diffraction pattern. The spots are sharp. If I stretch the contrast, now you can see actually there was a couple more spots there than we maybe saw in the first place. And if I zoom in on this boxed region here, this is what the data looks like in that region. And there's actually 1, 2, 3 spots in this diffraction pattern that you maybe would have not noticed at all when you were looking at the whole diffraction image here. Now, if I draw a line plot on the left image, you can see I'm drawing the line plot across the 3 spots I highlighted, but also additional spots in the pattern, and I'm showing it here on the right. And we can see that we can tell very well that there's these sharp peaks, although very faint, in the diffraction pattern here on the left. And then on the right is just the rest of the line plot plotted on a different scale. And so we can see that we can plot, we can capture diffraction spots that have, call it about 100 counts or so in this spot number 1 that looks very, very faint in the pattern there. But we can also capture very intense spots with way more counts in it, on this right-hand side of the line plot, which would correspond to sort of these really bright spots in images here. And so the sensitivity, the dynamic range of the camera enables you to do this, but also the frame control mode enables you to do this. Because if you were running at a long exposure time at a high frame rate, it would be really hard to see this spot number 1 and maybe even this spot number 2 here. So frame control is super useful for diffraction experiments. And I've been talking about the dynamic range of the ClearView camera. It's much higher than the OneView camera, in part because the sensor design has this HDR or high dynamic range sensor readout capability. So the dynamic range is much higher in general, going from the OneView to the ClearView camera, but also the ClearView camera design of the sensor has improvements in terms of the kinds of artifacts that you see in the diffraction pattern, both respect to crosstalk and saturation of the center spot. And whether you're using the OneView or the ClearView camera, I think you could always collect data without a beam stop here, as I'm trying to show on the left-hand side here of this diffraction pattern that was collected with the ClearView camera. And so just to highlight the differences here as well, going back to these 2 diffraction patterns between the OneView and the ClearView camera, if I draw a line plot here across the transmitted beam of both images and plot it, you can see that they're very, very different. On the left-hand side, one thing we can tell is that the transmitted beam of the OneView image is saturated because you have this sort of Gaussian shape you expect. There's a peak and then a minimum, and then there's this peak again here. And you can tell that it's saturating at relatively low counts compared to the ClearView camera. When we plot the line plot here on at the same position using the same imaging microscope conditions, there's no saturating in the center spot, and you can see that this Gaussian shape, or mostly Gaussian shape in the diffraction pattern, the diffraction spot, has much more intensity in it compared to the OneView camera. And so in this case, you're able to use a lower frame rate with the ClearView camera and not saturate the center disk at all in your diffraction pattern, which combined means that you're getting way better signal to noise and way better dynamic range with the ClearView camera compared to the OneView camera here. And so just to summarize, frame control is super useful, in my opinion, for both imaging and diffraction experiments with the ClearView camera. So that encompasses, whether it's an in-situ experiment or a 4D STEM experiment, as we'll talk about in the next section, or just very basic, selected area diffraction imaging as well. But one of the other ways in where the ClearView camera really stands out is the frame rate capabilities of the camera, which is up to 1600 frames per second. And so this is the plot that I showed, or sorry, the table I showed earlier in the presentation. And now I just want to highlight the comparison between the OneView and the ClearView camera. So at the maximum image size is 4K by 4K for both cameras, but the ClearView can run twice as fast. I think I've kind of mentioned this a little bit here and there already throughout my presentation, but the maximum frame rate is much, much, much faster here at 1600 frames per second compared to 300 frames per second. So it's over 5 times faster at the maximum frame rate, which means that you can do 4D STEM experiments almost 5 times faster. Now, you can note also here that the image size is a little smaller, but as I'll show in this next couple of slides, even at the 512 by 512 image size, the ClearView camera is much faster than the OneView camera, as you can imagine. So the way that we achieve these high speeds at different image sizes with the ClearView camera specifically is a combination of binning the image and then also using a smaller sub-area readout of the sensor. And so in both cases, you have less pixels to read out of the camera, which means you can read out frames much faster. And what this table just tries to show very quickly is the concept of how you can combine both of the binning and the sub-area readout to maximize the speed for your experiment. Or you can just use it as a way to inform how you want to generate data in terms of data rates, frame rates, image size, etc. And so the one trade-off that comes with using the ROIs is a smaller field of view. And so this is showing here on the right what the full ROI would look like. And then you have the half area ROI, quarter area, 1/8 ROI here. And so if you wanted to do 512 by 512 imaging for example, an in-situ experiment, you could do that at 800 frames per second with the ClearView camera. But if you were primarily interested in 4D STEM, which many people nowadays are, the 1/8 ROI is still really great for 4D STEM because it's a high speed and it's a smaller amount of data that you generate compared to the full area, which is very useful in terms of managing the data load that you generate from your 4D STEM experiments. But the idea in general is to remember that 1600 frames per second here makes the camera really, really useful and suitable and flexible for in-situ and 4D STEM data capture. And just to give you an idea of what the different frame rates look like, this is a very basic experiment where I've told the microscope here, just move 10 microns in one direction. And I recorded what that looks like with the ClearView camera. So on the left-hand side, we have a 50 frame per second image and looks pretty good. But if we wanted to slow down and try to see some more detail, at 1/10 speed on the left, you can see it starts blurring. Whereas on the right here, now I'm showing at 200 frames per second at the same speed, you see a lot more detail and there's no blurring and smudging in the image that's coming from essentially not being able to sample the data at high enough speed. And importantly, you can do 200 frames per second at a 2K by 2K image size. So it's a good frame rate and a really good image size compared to what was possible, for example, with the OneView camera and definitely with any kind of CCD camera from the previous generations as well. And when we do in-situ experiments in DigitalMicrograph with the ClearView camera, there's all sorts of tools here that I just wanted to highlight very quickly for playing back your data here on the top right, as well as doing different editing processes to the video, whether it's cropping the area in space or adjusting the start and end positions or doing additional binning or frame summing. All of those things are possible from your data to do within DigitalMicrograph on the raw data with all of the metadata associated with it to improve your data quality here and turn it into a really quick result. And so one nice, again, very basic applications example here was this video of this magnesium chloride salt that is currently being heated to 500 degrees Celsius. And so what we'll see here is that there's these little bubbles here that are being formed in the data, and we can see that the sample is drifting from the top right to the bottom left. And what you see here is this plot is the associated metadata that came from the in-situ holder that is linked together with your video data here. So it's a way of correlating the holder temperature data with your video data automatically within DigitalMicrograph and playing it back together. But the idea is that you can even take this video, drift correct it within DigitalMicrograph, and then get a very nice result here where we can just look at the motion of these bubbles within the magnesium chloride salt at high temperature without having any drift in the image at all. Still at a high speed with high resolution from the camera. But I keep talking about 4D STEM again in terms of speed, and I think that's because the ClearView camera is really nicely positioned for doing 4D STEM experiments, and it's something that a lot of people are really interested in doing in terms of a technique. Because when you combine the ClearView camera with the STEMX system from Gatan, which is what's used for doing 4D STEM experiments, you have the ability to do all sorts of applications here that I show on the right. You can do virtual aperture imaging, differential phase contrast or DPC imaging. Now we can do orientation mapping and diffraction pattern indexing. You can do strain mapping on a sample. You can do in-situ 4D STEM experiments. And then you can do really advanced things like custom scan patterns, etc., with this 4D STEM technique and a high-speed camera. And so high speed is always really good for 4D STEM because it affects the data rate at which you can acquire 4D STEM data. So this is just a comparison of what that might look like for the ClearView camera versus the OneView camera at the maximum speed that's achievable. So here we're just acquiring a 4D STEM data set of this semiconductor sample that I showed previously in the experiment. And this would take 41 seconds at a 256 by 256 mapping area with the ClearView camera. And I played it back twice as fast so we wouldn't have to wait here. But of course, now we're done, and the OneView is about 5 times slower. And so we'd have to wait a long time to capture this data. And in a technique where you're trying to maximize your throughput, and if you want to do in situ results or experiments, the frame rate is super important because especially for an in situ 4D STEM experiment, the time it takes you to acquire one pass of the 4D STEM map area is what your time resolution is for the 4D STEM experiment. So if you're interested at all in doing in situ 4D STEM, then the ClearView is a huge advantage over the OneView camera just in terms of its speed and what's possible. And these next two examples are just really nice examples showing how we can do, for example, 4D STEM analysis via strain mapping on thin films. So this was strain mapping you can do within DigitalMicrograph, or you can use open source platforms like Pi4D STEM and PixSTEM to do strain mapping. But in this example here, they had this nickelate film that they grew on STO, and then they were trying to reduce the nickelate film on top. And the way that they could look at the level of reduction of the nickelate film was to see how much strain there was in the material at different levels. And so the idea is that they did a strain map and they plotted the strain profile across the multi-layers kind of interfaces, and they could see this changing level of strain in the nickelate film, which corresponded to an incomplete reduction of the nickelate which they were looking for. So they're still doing more work on this sort of growth mechanism and reduction mechanism for these nickelate superconducting films, but the strain mapping was a really good way of getting at the level of reduction here that you can do. And then something else that you can do again in 4D STEM that I think is really great, it's a new capability for Gatan and DigitalMicrograph, is ability to do orientation mapping and phase mapping. And so this, for example, is the diffraction pattern that came from the ClearView that was actually acquired using precession microscopy technique that we're developing here at Gatan to acquire precise diffraction data for 4D STEM. And we can do diffraction pattern indexing on all of the patterns within the 4D STEM map that we acquire, and then do the orientation mapping and phase mapping. In this case, this is stainless steel. And so we have the austenite phase and the ferrite phase that we can index and then map out really nicely here with the ClearView camera and the tools within DigitalMicrograph for 4D STEM. So that is pretty much the end of my presentation. There's 10 minutes left in the hour. So I just want to, again, reiterate the fact that I think the ClearView camera represents a really big step forward in terms of what's possible with Scintillator cameras for maximizing the signal to noise for any kind of experiment with a frame control mode, and then also really utilizing the high-speed capabilities of the camera to get really good in-situ data and 4D STEM data as well. And so as I summarize here, I just want, again, say that today's modern cameras are using CMOS sensors. Many people, I think, still use the word CCD colloquially, but it at sometimes can be unhelpful to use that term because it's so far behind the current technology nowadays. And having a high-speed CMOS sensor means that you have a lot of ease of use capabilities that pop out of that, like drift correction and the ability to do high-speed experiments like 4D STEM and in situ. And as more and more people want to do low-dose imaging and faster experiments, that's what's driving the development of hardware for Scintillator cameras at Gatan, but any other kind of Gatan camera that we have available, whether it's a direct detection or hybrid pixel, etc. These are the things that we have in mind of where we're going with the camera technology. And things like the frame control, how you can operate the camera and use the smaller sensor ROI areas with the camera to maximize the speed. All those things are things that were also available on the ClearView and we're moving towards and for future cameras that we develop as well. So that's the end of my presentation. If you have any questions, I'll remind you that you can enter them into the question pane of the GoToWebinar interface. And as the final comments, that if we don't get to your question today, they'll be addressed offline. I'll send you an email with an answer to your question. And the recording of this webinar will be available within the next week or so on the Gatan website. So you can watch it again if you had any interest with that. So thank you so much for your attention today. And I'll take any questions now.
Thank you, Fernando. We have a few questions that have come in. So the first one is what type of scintillators are you using for these experiments?
Good question. So the scintillators we use, it's an organic phosphor material. I think any more detail than that is proprietary, unfortunately. But it's the kind of scintillator that there's a lot of different materials I can use and processes you can do to change the properties, like the thickness of the scintillator, etc. But the one that we use in the ClearView is similar to the one that we used with the OneView.
Okay, and then the next one that came in is what is the physical pixel size of this camera?
The physical pixel size of this camera is 15 microns. So the pixel size of the ClearView camera and the OneView camera is the same. It was 15 microns as well. And then I talked about the UltraScan and the Arias. The UltraScan was, I think, about 14 or 15, and then the Arias was 9. So you have a larger pixel size and a high amount of pixels with the ClearView camera, which means that you can get a very wide field of view on the camera.
Okay. Next question that came in is your last example showed 0.7 degrees precession diffraction, so PED. PED may be rather complex to, I think it's a line. Do you have a special software in STEMX for precession alignment?
Yeah, so right now we're developing this plugin for precession for STEMX that can do these kinds of precession experiments. The way that, this is a question maybe that's better answered offline that I can send you some more detail, but the plugin, essentially the way it works is that it involves a series of simple calibrations that you can do within DigitalMicrograph without the need for any additional hardware. And then DigitalMicrograph can control the microscope to the level needed to maintain everything in alignment as the beam is tilted for you to do a precession experiment. So we're working on it to be user-friendly, easy to sort of maintain in alignment. And it's a capability that is under developing, but we're starting to talk about it. So I'll shoot you an email, and if you have any more questions, I'm happy to talk about it.
Okay. And then another question that came in is can you compare and contrast the ClearView with the Stella, Alpine, Metro, and K3 cameras?
Good question. So the K3, Alpine, Metro, those are direct detection cameras. And so direct detection cameras, I didn't talk about it in this presentation, but it doesn't have a scintillator, and that makes it more sensitive. In addition to the fact that they can do what's called electron counting, which is an image processing method of removing the read noise and other sources of noise from the image. So you get very good signal to noise, very high sensitivity, much higher sensitivity than scintillator cameras. And so in general, those cameras are really well suited for low dose experiments, low dose imaging. You know, in the biology world, it's huge because people are looking at proteins and small molecules, which are extremely beam sensitive. And so you need the sensitivity of a direct detection camera to do those kinds of experiments. And then within the material science world, you know, if people are looking at 2D materials or MOFs or other very beam sensitive materials, it can be a huge advantage to switch to a direct detection camera as well. And then the Stella camera is a slightly different version of a direct detection camera. It's what's called a hybrid pixel camera. And hybrid pixel cameras, their main advantage is that they have huge dynamic range and really, really high speed at the trade-off of a smaller image size. So typically, the Stella camera is in its most popular format is like 512 by 512. So those cameras are really, really good for diffraction experiments. They're a little more niche in that sense. So if you are super interested in only 4D STEM or only micro ED or only diffraction in general, then Stella and hybrid pixel cameras in general are really, really powerful in that case. There's no, what I'll say is that there's no one camera that is good for every application out there. The ClearView camera and Scintillator cameras are really good cameras for people who are trying to do a lot of different things on their microscope. But as soon as you feel like, oh, I need better sensitivity for low dose imaging, then I would always suggest take a look at a direct detection camera. And as soon as you think, oh, I need the ultimate speed and dynamic range for my 4D STEM experiment, then I would say take a look at Stella and hybrid pixel cameras.
Thank you. And then last question that we'll take online is, can you comment on how these advanced scintillators can help in viewing the nano-sized multi-phase composites? And how can we look the short range order of materials, like in battery electrode materials?
I see. I think if you're trying to do phase mapping with, you know, you can get at phases either the elemental way by doing EELs or EDS, or you can try doing orientation mapping through 4D STEM. Or if you're trying to do like look at short range order, a lot of times people want to look at the diffraction patterns from the data that they acquire and then do some kind of analysis of the diffraction pattern to get at that short range order. In either case, what I'm trying to get to is having a camera that's good for 4D STEM, has high dynamic range, and good signal to noise will benefit all of those applications. And those are things that you can do with the ClearView camera and also with the 4D STEM packages that to acquire 4D STEM data that Gatan has as well.
Thank you. So for any other questions that come in, we will definitely try to reach out to you offline and answer them as appropriate. Thank you, Fernando, for the lovely presentation today. And if you guys have any other questions, feel free to reach out. We will be sending the recordings out within the next week for offline viewing. Thank you.